So welcome all to the 6th Colloquium of the LatentView Colloquium series. We're very grateful to Mr. Gopi Kotishwaran, our alumnus and former CEO of LatentView, for generously funding this Colloquium series. And the long line of distinguished speakers, today we have with us our RBCDSAI Distinguished Fellow, Professor Srinivasan Parthasarathy, who is a professor of computer science and engineering and the director of the data mining research lab at Ohio State. This research interests span a wide range of topics, including data analytics, database systems, and a lot of high performance computing as well. He's among a handful of researchers who won both the DOE and NSF Career Awards, and he has a very distinguished set of achievements. He and his students have won 10 plus best paper awards or nominations from many top conferences, including the WebConf, SIAM Data Mining, ACM SIG-KDD, and so on. And he's chaired the SIAM Data Mining Conference Steering Committee till 2019, and also serves on the board of several journals in parallel computing, machine learning, and data mining. And since 2012, he's also helped lead the creation of OSU's nationwide first undergrad major in data analytics, and is one of the founding directors. With that, very happy to have you here, Srini. We're very excited to listen to you. Srini is going to talk to us about scaling graph representational learning algorithms in an implementation agnostic fashion. Over to you, Srini.
Thank you, Karthik. Let me go ahead and share my screen. Hello, everyone. Can you guys see my screen?
Yes.
Yes, we can, yeah.
Awesome. Okay, so I'm going to get right to it and talk about this, explain some of the words in this title as we go along. And Karthik and Ravi, thank you very kindly for the invitation and the very nice introduction. So let's get right to it. This should come as no surprise to people who know me, and especially folks in this crowd. You know, oftentimes when I see a problem, I think about abstracting them out to graph form. But here, let me try to explain why that's such a nice abstraction and sort of why they are so ubiquitous in, you know, modern data science and machine learning algorithms. So you have, you know, ranging from social networks to biological networks to road networks, analyzing these graphs impact pretty much all walks of human endeavor. So they show up everywhere, and the types of analysis that you would like to perform on these graphs, of course, will vary depending on the application domain, depending on the domain scientist preferences, and so on and so forth. So there's going to be a lot of variety in the types of analysis that one is likely to see in this space. So, for example, if you wear a database hat on some of these problems, there are a number of different things database folks, data mining folks are interested in, including, for example, mining frequent graphs, mining molecular graphs for bioinformatics and drug discovery problems, motif extraction, clique detection, subgraph querying, and so on. At the same time, if you're an ML engineer and you're looking at some of these graph problems, you're interested in, you know, things like how do we best represent this graph? You know, we as a community are, you know, very familiar with vector-based representations. So how can we convert them? How do you predict what link is going to form in the future? How can we classify certain properties of these graphs, and so on and so forth? So there are basically a range of different analysis that one can perform on these kinds of graphs. And there are sort of two overarching considerations or challenges that people have to consider when analyzing such graphs. First of all, they can be very large. They can have certain types of topological constructs that are pretty unusual and different from what they've been used to. And of course, from the user's perspective, there's also the fact that they come into these problems with different skill sets. So domain users may have their favorite programming language. They might be comfortable programming in R or Python or Ruby on Rails or Java or C or C++ or assembly or some kind of esoteric language. So they come in with different skill sets. And if you want to consider the productivity of the domain users, you have to think about how a system can support some of those things. And on the other side of the equation, you have to think about performance consideration. That is, how effective is the quality of whatever you're doing on the downstream task that you want to run these analytic queries on? And also at the same time, how can we best take advantage of what the underlying architecture gives us, especially given the modern world where architectures are increasingly heterogeneous? Just to back up a little bit about my background, I come to this problem both from the perspective of a machine learning data mining person as well as a systems person. Most of the talks that I've given at RBCDSAI in the past have focused on machine learning aspects. This talk is going to have a little more of the systems aspect of things. So I hope you guys will bear with me as we move through these. So as I said, we have a lot of these different types of analytic queries. And so the overarching question as a systems person is, can we eat our cake and have it too? And essentially, as I said, there are these two somewhat distinct classes of types of querying. And so trying to unify all of them under one umbrella is definitely possible and something we'd like to eventually get to. But for now, I think we're focusing on them as separate sort of elements. So the Fractal project that I've been fortunate to help us oversee is a project that handles the first type of queries, the more database-oriented queries. And this was our initial version of this was presented at SIGMOD a couple of years ago. But today's talk, I'm going to focus more on the graphs and ML side of things. And specifically, we're going to talk about a system called MILE that focuses on graph representation learning. So that's to provide context for where we're going to be going in this particular talk. But both of them share several attributes in terms of, both of these systems share attributes in terms of productivity and performance. So focusing on the second task, we are looking at, again, as I said before, our focus is on graph problems, and graphs arise in different perspectives. They can have unique topological characteristics. They could be bipartite, for example. And there's a lot of downstream, things a domain user would like to get out of these kinds of problems. And so, for example, you'd like to be able to classify certain properties of nodes, maybe recommend something to a user, and so on and so forth. And oftentimes what we found in recent past is that there's a lot of these network representation learning or graph representation learning methods result in state-of-the-art performance on these downstream tasks. And so our focus is going to be on looking at these kinds of graph representation learning or network representation learning problems. So what are these? So at a very high level, a graph representation learning method takes an input graph, as you see on the left side, and produces some kind of vector representation of the nodes. There are some constraints, and we'll talk about some of those constraints that you'd like to achieve. You'd like nodes that are close enough in graph space or network space to be close enough in the vector space. So that is an obvious one that we'd like to keep into account. And the idea then is that these node representations can then be directly leveraged to analyze downstream ML tasks. So they can act as sort of features in downstream ML tasks. And so that's sort of the general principle under which we're operating for today's talk. So moving right along, what are some of these constraints that we'd like to be able to keep? So as we pointed out in the previous slide, these try to learn representations of nodes. And you'd like to be able to make sure that the similarity between nodes in graph space approximates the closeness between nodes in embedding space. There are other constraints that you may want to capture as well. But for now, for the purpose of this talk, at least, this might be good enough for us to keep moving. But there are other constraints that folks can look at. And certainly some of those aspects are being looked at both by my lab and others in other labs as well. So no surprises here. There have been an absolute plethora of techniques. This is a diagram from a paper that was put out on arXiv in 2000 and in 2020. And it basically talks and characterizes and categorizes the different types of graph representation learning that people have looked at. Now, for the purposes of this talk, we are going to be largely focused on unsupervised graph embeddings, but there are some ideas that we have deployed in other contexts for both supervised and semi-supervised, as well as self-supervised learning. But I'm not going to talk about those kinds of things today. So the current state of art is that you have a lot of techniques, but very few of them are not very scalable. They take a lot of time to learn these representations, or what we sometimes will refer to as embeddings. I'm going to use representations and embeddings interchangeably in this talk. So for example, on a graph with about 1 million nodes and 3 million edges, a moderate sized graph, on a machine, I wouldn't call this machine state of the art today, but it was state of the art maybe 2 years ago, with about 128 GB of RAM. It takes about 15 hours to compute on a particular representation learning method called node-to-vec. On a different method, it does not even finish given more than 2 days. So on graphs with much larger number of nodes and edges, embedding techniques simply are not going to be able to perform on modern architectures. You're going to have to rely on distributed or parallel, much larger systems. And this is problematic because some of these see uses in very day-to-day occurrences, and not everyone can afford to run these things on a supercomputer, not to say anything about the energy costs or other considerations that some of these models take to train and so on and so forth. So what we'd like to be able to do is, can we scale these techniques? And this is where, we sort of my systems hat, I put on my systems hat and asked the question, can we scale it in an agnostic manner? Because we'd like to let people produce their algorithms in the programming environment that they're most comfortable programming in. And ideally, we'd like to be able to scale this without impacting the quality of the results. And moreover, maybe there's an opportunity to actually improve that quality. And I'll talk a little bit more about why we have that opportunity with the approach that I'm going to describe. So that sort of sets the stage for the problem. Our solution is MILE, and a distributed variant of this called distributed MILE. MILE stands for multi-level embedding. MILE is a framework. It is not an algorithm. It takes existing algorithms that look at unsupervised graph representation learning techniques and scales them in an agnostic manner, and oftentimes improves the quality of embeddings in the process. And I'll talk about why that is in a few slides. For example, and this is just simply to give you an early preview into the results, if you take a popular method called node-to-vec on a graph with 3 million edges, it takes 15 hours to compute on the machine that I just described in the previous slide. Whereas if you apply it with MILE, you can get the same thing done in under an hour, in fact, about 35 minutes, all while improving the quality of the learned embedding. So not only is it faster, it also improves the quality. And this is while the user can program this in whatever programming language they desire. So that's what we're going to talk about. So now let me give you an overview of the process underpinning MILE. So the process is as follows. It follows a coarsening refinement strategy that has been leveraged for graph partitioning algorithms for at least 2 decades or more, actually more. And it essentially follows this strategy where you take a large input graph, G0, and you iteratively coarsen the graph down to a level that you're comfortable with. Let's just call this G subscript M for now, for notational convenience. And then you apply your whatever embedding strategy, graph representation learning strategy on this base representation. And then you refine this back so that you get the embedding for the full graph. And so these are the 3 stages. 2 of these stages are completely agnostic to the graph representation learning algorithm that you're going to use. They only depend on the graph itself. Well, one of them, the graph coarsening stage, depends only on the graph itself. The embedding strategy that you deploy will run on this coarsened version, and then you have the opportunity of refining it, taking into account both the graph structure that you learn through the coarsening process, as well as some information from the embedding strategy. So this is a good sort of point for me to see if there are any questions in the audience. Could try to take some quick questions before proceeding with the details of each of these different steps. Ravi, are there any questions?
No, none that I can see. Yeah.
Okay, sounds good. So folks, if you have questions, just please go ahead and put them in chat or something like that. And I will stop at strategic points in the talk and try to take them as they come. Moving right along, I'm going to talk about each of these different phases. And we'll start first with talking about graph coarsening. So given an input graph G0, the idea is that we repeatedly reduce the size of the graph. And this includes both the edge set as well as the node set in this case. So you essentially come up with a series of graphs, G1, G2, all the way to Gm, such that the number of vertices in each of these is reduced, and also the edge set, which I'm not showing here. And these graphs form a hierarchy where G0 can be considered at the top, while Gm at the bottom, like I showed in the figure previously. So the questions we had were how to best coarsen the graph and what criteria should we use. And here's where that criteria, that constraint that I talked about earlier is kind of important. We want to make sure that nodes that are close in graph space remain close in embedding space. And we're going to try to take that intuition into account as we think about how we're going to do the coarsening process. So, so the first thing we're going to do is, and I've got an example here with 5 nodes and graph. We have edges and they could have weights on them. They don't have to. I've just taken a simple example of, a weighted graph with weights equal to 1 for each edge. So if 2 vertices U and V are structurally equivalent, then we'd like to be able to match them as part of this coarsening process. And so by structural equivalence, I'm going to try to explain what that means through this moving example here. So in this example, you have nodes D and E that both connect to A, and that's the only edge they possess. So they have this structural equivalence that they are exhibiting in this particular graph. And so what we try to do is take such kinds of examples and we try to merge them into what we call a supernode, illustrated on the right side of this animation. Note that what we also do is add up the edge weights. So each node is contributing an edge weight of 1 to the resulting connection to A. And so we have this weight of 2 associated over here. So this is good. But then now you have the question that if you look at the triangle at the bottom, all of them have similar sort of edge weights. So how do you decide which pair to sort of go at next? And so this is where we rely on a secondary mechanism called heavy edge matching, normalized heavy edge matching. The idea is that you pick an unmatched node U and select the heaviest edge, and the weight of an edge is determined based on the weights of the individual edges. Pick an unmatched node and select the heaviest edge on it, say UV, and match U and V if V is unmatched. The problem with that, as we illustrated in the previous example, is that all of these have the same weight. So we need a way to separate that out. So one way to separate that out is to take into account the degrees of the incident nodes on the edge. And that's the procedure that we adopt at the bottom through this formula here. And so again, if you go back to the same example, this is what that weighting mechanism is going to give you. And then you connect the ones that are closest to each other, that have the highest weight. And in this particular case, that's going to be B and C, and you're going to have a result like the one here. So the normalization procedure allows you to essentially break ties more meaningfully in order to get this resulting coarsened version of the graph. Now, one thing to note here, and this is for mathematical convenience, but the interpretation here is that both B and C have an edge of weight 1, and that's why you have this loop here to represent the fact that B and C have, you know, a weight 1 edge with each other. And I'll get to why mathematically this makes sense in the next slide. So if you think about this procedure that we have described, this can be represented very neatly in matrix algebra. So basically, if your original adjacency matrix is described as A0, and we have this matching matrix that basically tells you which nodes in your original graph are being mapped to which nodes in the coarsened graph, then you can derive essentially the adjacency representation of this through this particular operation, simple matrix multiply operation through this process. And so this combination of structural equivalence matching and normalized heavy edge matching gives us a procedure, a process for how to bring the graph size down from G0 to Gn. And so we go through this process iteratively. You can think that each iteration or each level typically under expectation will reduce the size of the graph by about half its original size. And so each level actually gives you a substantive reduction in the graph size. I will stop to see if there are any questions at this point. Karthik.
Yeah, so there are a few questions. So is the coarsening process somewhat similar to how message passing works in a k-sized neighborhood of a node? Just one question.
Not quite. I mean, it's related in the sense that we do get some of these higher level interactions, and I'm going to talk about that benefit shortly, but it's not quite the same thing in terms of the procedural process. And I'll be happy to answer that in more detail later on if there are further questions on that.
Okay. And what about the data loss during graph coarsening?
So that's a great question. So we are retaining, so a couple of things, let me just make it clear. For each step, we are retaining the matching matrix. So we actually do not lose the structure of the graph anywhere through this process. We always have these matching matrices as we go through the process. But there is a non-trivial chance that because of this coarsening procedure and whatever you do on the coarsened graph, that you may lose some important information. And that is definitely possible. We try to avoid losing as much information as possible through this sort of structural equivalence class matching and normalized heavy edge matching. But it certainly is possible that you can lose some information, but we also, here's the important point, we also gain some important information in the sense, and this is related to the first question, in the sense that when you are operating the embedding strategy on the coarsest version of the graph, you have much more information about the global topology, which you often miss out on with various graph representation learning algorithms, because they don't operate on it. They're very much a local oriented approaches, most of them. So there is an advantage also. So through this process, you can both gain up to a point, but after a point, you might lose a little bit of information. What we're trying to do is minimize that loss, but that's a great question.
Okay. And is it necessary to examine the blank spaces while also considering the cosine portion?
What do you mean? Let's take this later, because I'm going to need clarification on what blank spaces are.
Okay.
So let's take that one later. Yeah.
And there's a question about if you could explain the denominator weight calculation.
Again, this is probably asking a more detailed question, so I'll hold this for later. Yeah. Okay. Yeah.
And there's a question on the rules for graph coarsening, and I think maybe this also we can discuss it.
So the rules for graph coarsening are basically the two things that I described: the structural equivalence matching and the normalized HEM, and both of them at some level are trying to capture that sort of constraint. That you want to make sure that representations learned in vector space are matching with representations that you would expect to see in the graph space. So distances are relatively similar in both spaces. Okay. All right.
Yeah.
So I'm going to go ahead and proceed. And as more questions arrive, I will stop again. So we've got these. So the important thing to remember, as in response to one of the questions I said, is that through this coarsening phase, we have retained everything we need in order to get back to the original structure of the graph. So we have our adjacency matrices for each intermediate step, and we have the matching matrices that allow you to go from one iteration, so one level to the next. So technically, you only need GM and all the matching matrices, and you can compute G0 from that. So it's easy to show. It's just a series of matrix multiplication operations that have to be inverted. So now we have our base embedding, and this is where we rely on folks to use whatever programming language or programming environment they're consistent with. All we ask is that they feed in our GM to their algorithm or their approach and generate what their method would produce from GM. And that's the only part where we're relying on them to apply their approach and run it. And so, for example, you could run it using Deep Walk implemented in any language. There are implementations in C, Fortran, Ruby on Rails, Python, and so on and so forth. You could use GraRep. You could use a host of different techniques. So there's no restriction on the kind of embedding technique that can be used for generating the embeddings or the type of programming environment. So users can be highly productive in the sense that they can use whichever programming environment that they are most comfortable with. The only thing we need is that they need to run their algorithm on this graph GM. Now, here's one of the reasons why this approach is relatively efficient, is that by the time you've reduced the graph down to GM, the graph is tiny compared to what it was originally. And so, because at each level, you're reducing the size of the graph by roughly half its size. And so by the time you're at GM, and GM you can choose at an appropriate level, you're actually comfortably fitting GM in your closest cache. So it often fits in L1 for most computer architectures, modern computer architectures. You can even set this up to be stored in a edge device, which has much smaller memory support or cache support. And so you can actually control for this so that it can be run in a distributed setting on the edge. And so you can control for the size of GM through this process. And so this is where we get the main benefit. That is, even if you have a slow algorithm, an algorithm that takes a lot of time, because we're able to reduce the graph down to this tiny graph, you can run your method on this and produce a result, and then pass it back to the MILE framework, and it will take care of generating embeddings for the original, much larger version of the graph. The other advantage, as I mentioned, as part of an answer to the first question, is that you have access to non-noisy global view of the graph. We've seen this we've seen the benefits of this in various graph partitioning algorithms. We've seen the benefits of this in stochastic flow algorithms, which is related to the message passing question that I got. So it does model higher order interactions in that general sense, but the specific implementation or the approach is slightly different. And so, but at the end of the day, because it has access to this global view of the graph, you can actually learn higher quality embeddings through this process. So that's the base embedding, and that was pretty easy because you're just going to let the user run the whatever approach they want on the base on this graph G subscript M, and then they can produce the embeddings for that using their method, using their programming languages, and that is all we need in order to feed it back to the rest of the MILE system or framework. So now comes the most interesting part of MILE, which is the embedding refinement phase. And so here we now have to take the series of coarsened graphs that we have and the corresponding matching matrices, which we have, and the node embeddings that EM on GM produced by the base embedding algorithm on GM. And our problem is to generate the embeddings of the original graph G0 from this embedding that we have of GM, which is EDA over here. So this is our problem statement. The simple solution is to take, just project the embeddings back, from the current graph to the graph above it in the hierarchy. So this animation sort of gives you an idea of how something like that might look. So whatever you've coarsened, so BC had been combined, DE had been combined, you take the representation you learned for the supernode DE, take the representation you learned for the supernode BC, and apply it back down to the elements that you coarsened it on in graph GM -1. So this is a solution. Now, and it is a starting solution, but the problem is at the end of this process, you may have a lot of nodes with identical embedding representations, and that doesn't necessarily reflect what you're seeing in graph space. And so, and if you apply this iteratively, by the time you reach G0, you're going to have, hundreds of nodes in your graph, especially if you start with a billion node, trillion edge graph, you're going to have thousands of nodes with the same representation through this process. And that's problematic, and that we don't want. So our strategy here is, can we take advantage of the power of graph convolution network models? And we have a very specific reason for choosing this particular model. And I'll try to talk you through why we look at that particular thing. So at a very high level, the refinement method, for each iteration, you want to get from input of embedding at level M to output, which is the embedding at level M-1. And so first, we apply a simple projection like I showed you in the previous slide, but we don't stop there, okay? We don't stop at that point. We then run this projection layer through an L-layer convolution, graph convolution network. And this is where we start to see the benefits of some of the ideas one of the questioners had about message passing. We are starting to take advantage of higher order interactions in the graph through this particular process. And so this can be represented using mathematically, as the formula below here shows. Sigma is a standard, ReLU nonlinear operator. What we are using here is essentially a Laplacian, a normalized Laplacian, and it's applied to so for each layer in this process, the output of the previous layer is fed as input. And then theta k is a weight matrix for each layer that we learn. It's a d by d weight matrix. So it's a standard GCN representation for those of you who are familiar with graph convolution networks. Now, a couple of things I would like to note here. Why did we choose GCN? Well, take a look at this Laplacian, normalized Laplacian here. And if you go back and think about what we're doing with graph coarsening, we are taking these, if you go back and look at this representation that I have over here, we are taking the degrees of the incident nodes into account. Take a look at what the graph convolution network is doing in terms of what it is computing in this part. And we are taking, again, in this context, we're doing, we are basically taking into account what we used in the coarsening approach. And that's part of the reason why we think this method works better than some of the alternatives that we tried out. We did try out some other alternatives, and it matches what we did during the coarsening phase. And so this is the intuition. This is not a theoretical proof, but this is intuition as to why this method works well for us. Now, we're not done here. So one possible loss function for modeling this is to take into account how far you are from what you're predicting from the actual. So the actual being what you have running on the base embedding method for the previous step or the previous coarsen step versus what you're producing through this graph convolution network. Now, there's two problems with this. One, if you have to generate embeddings twice on both GM-1 and GM, that's adding expense to your overall time you're running this method. The other problem, which is for which a fix is more expensive, is that the embeddings you learn through this process on two separate things may sit in different spaces. They may sit in orthogonal spaces. And that's a theoretical issue that you can come up with a fix for. There have been fixes for it, but it's expensive. Okay, so can we do something else? And it turns out we can. We can basically train the model on GM itself directly using a matching matrix of an identity matrix and learn theta k that we needed, the weight matrix for each of the layers in the L-layered graph convolution network. We can learn this theta k for each of the layers using the base itself. And this was a bit of a sleight of hand approach, but it turns out that this loss function actually works quite well. And there is some theoretical justification for this, which I'm not going to present here, but there is some theoretical justification that others have also presented for these kinds of ideas, not just us, for what we're doing here. So now what we have through that process is we avoid both of these concerns. We don't have to generate ground truth twice, and we don't have to match the embedding spaces because we're operating in the same embedding space through this revised loss function. And we can learn theta k, the weight matrix for each of the layers in the graph convolution networks. Now, once you have those theta k those theta k weight matrices, you can then use them directly for each of the subsequent stages during the refinement process. And it's simple matrix multiplication at that point. It's a relatively inexpensive refinement. And so the embedding of graph GM-1 would be generated through that graph convolution network, where input is the projections, the initial projections, and the corresponding adjacency matrix of the graph, and the output is the embeddings at level m-1, and then you have to iteratively go through this process all the way until you can generate the embeddings for the original graph G0. So that's at a very high level. That is procedurally what we are doing for MILE. So this is, again, Karthik, this is a good stopping point for further questions. So I can take a few more right now.
There aren't any new questions.
Okay. All right. I will continue and then try to answer the ones remaining at the end. Sounds good. Okay, so the embedding refinement step was, I think, at least from our perspective, involved the most creative elements for what we're doing. One thing that I want you to understand in this intuitively, which I didn't mention before, is that this embedding process, this refinement process, learning the graph, the parameters of the graph convolution network, it's important to understand it learns both from the graph structure itself, but it also learns something about the embedding process that the user has provided, the base embedding or representation learning process. So it takes into account both structural information through this refinement process, but also takes into account certain elements. It learns certain elements of the embedding strategy. So when we look, for example, at the weight matrices, the theta k's that are produced through this learning process, we can see that for the same embedding method, but for a different graph, those weight matrices are different. For the same graph and different base embedding methods, those weight matrices are different. And so it's learning from both of those. And that's very, very critical to make sure everybody understands the power of this approach. So it's learning from both the graph structure and the base embedding in this process. So now I'm going to give you a sense for this using some popular embedding graph representation learning techniques, but it's the method is not limited to any of these. And these have been implemented in a variety of different programming languages, some in C, some in C++, some in Java, some in Python, many in Python, actually, and so on and so forth. And our purpose here is to evaluate both the scalability and the quality of the generated embeddings. So let me start with this first. And let me give you what the values are here. So the x-axis represent the different levels. So G0, G1, G2, G3, G8. And at G0, what we are showing is the performance of the algorithm that I have within brackets here. So in this case, it is deep walk. The performance of deep walk without MILE. G0 represents ground truth without MILE. And then G1 through G8 represent performance using MILE, but with using deep walk as the base embedding. And so you can see that for all of them, there is a jump up initially because the coarsening allows you to get more global information. So there is an improvement. And so y-axis is micro F1, which is a standard evaluation of node classification quality. And so higher is better. And so in almost all of these, you see a jump up. So with respect to what the approach performs on just the raw data, the original data. And then there is a little bit of loss, as one of the questioners astutely pointed out, there is some loss, but the loss is minimal. So for example, for both node to vec and deep walk, you do not get to, you are still above the original performance all the way up to level 6. It may not be that obvious on the slides, but all the way up to level 6, you're above. At about level 7, you're equal. And at level 8, you tail off a little bit. You lose maybe a percentage point or something like that in performance. Now, what does that translate into performance in terms of computation? What you see here is that it dramatically, y-axis is time in minutes in log scale. So small change, I mean, a small change here represents really a large change. It's almost an order of magnitude. And so for each level. And so by the time you reach to 6 and 7 for node to vec or deep walk, you're running in the order of, a few minutes, essentially. You're running at the level of a few minutes versus something that takes over 1,000 minutes to run in this case. And so this is on a smallish data set. So this gives you an idea of, you're not losing much in terms of accuracy and you're gaining a lot in terms of speed. And all while implementing these things potentially in different programming environments. Now, what happens when you scale this up even further to a much larger graph? Same result. Basically, you don't see much of a, you see some improvement when you start coarsening. You see a little bit of tail off. There is some loss in information, but the loss in information is minimal. It's a fraction of a percentage point in this case for almost all the methods in terms of quality. But when you see a dramatic drop in terms of the time it takes to perform on this data set. It's quite dramatic. Remember, again, this is on a log scale. And each of these, again, represent the different levels. So G22, G2, and so on and so forth. So the net result is that we don't lose too much quality. In fact, we gain quality in some cases. And we see orders of magnitude improvement in the performance of the approach. And we see similar results also for link prediction. I mean, we showed it on node classification, but the results are very, very similar for link prediction as well, again, for a wide range of different problems. I'm going to, there's nothing, I mean, it's just a different, there's a different measure of goodness or quality, which is the area under the ROC curve in the case of link prediction. And again, results are quite similar. You don't see a dramatic drop. In fact, in some cases, you see an improvement, a steady improvement because of this process. Again, we see a significant drop in terms of the time it takes to run these kinds of algorithms. So again, orders of magnitude. Again, the y-axis on the time charts are in log scale. So if we look a little more deeply at this, I think if you look at algorithms or approaches, and this could be a function of the algorithm, it could be a function of the implementation language. So if you have something that uses a lot of memory, we see substantive gains in terms of reduction in the memory as we move along. So you're seeing this here with something like GrapRep. And similarly with matrix factorization methods like NetMF, you see a similar reduction, although the scales here are quite different. GrapRep uses a lot more memory than many of the methods we look at. And so for those methods, we see a substantive improvement in terms of the reduction. And because you're reducing what you are using to represent the graph, and things start fitting in L1 or L2 of your architecture, you are benefiting dramatically from locality. And this is, a principle that we all know quite well, the principle of locality. And so you're benefiting from that. And that's, that is a direct attribution to why we're seeing the scalability results that we are. So the results that I gave you in the previous slide are all, or previous slides are all on a single node machine. And so what I'm going to talk about now is, can we improve the speed up even further? Essentially, can we take advantage of what we can get from the power of distributed computing? Now, key thing here is that we don't want to touch the middle step, because the middle step depends on, the user's programming environment and the user's convenience. So we're not going to touch that step. So we're only going to speed up the coarsening and refinement process. We're not going to touch the base embedding step. And so whatever results you're going to see here are really focused on improving the scalability of those other two steps. Because we still want to retain the productivity advantage that we have. So the main difference between MILE and distributed MILE, I'm going to try to go through this a little quicker because I don't want to go over time. The main difference between MILE and distributed MILE, both are general purpose and both exhibit little loss in quality. The only difference is that we try to do this in parallel. And I'll talk about why parallel instead of distributed, because we did an analysis. And it turns out that for graph coarsening, you prefer a shared memory model, an OpenMP, if you're familiar with OpenMP and MPI, versus an MPI-based distributed model. And this has to do with the amount of work involved, and also has to do with the structure of the graph that you have to take into account in this case. And so, again, a couple of small notes here. MILE uses a hash table to quickly find matching. I didn't get into this implementation detail. Distributed MILE uses parallel locality sensitive hashing. We have some work that we've done in the lab in this space, and it was very easy to just leverage some of our own work in this context. And so this was a minor difference. For normalized heavy edge matching, we rely on an idea that LaSalle and Karpus proposed, to use a version of unprotected matching first and then correcting the conflicts via post-processing. So the conflicts that arise are basically if the same node is being matched to two separate or distinct nodes, then what do you do? And so there's a way to resolve that LaSalle and Karpus proposed. We essentially use what they suggested in that context. And we compared a parallel versus distributed version of this. And it turns out that the distributed version, the overheads were just too high in order to do it for the kinds of graphs that we were looking at. And maybe this changes if we look at much, much larger graphs than we did. We looked at up to 100 million edges. But right now, at least, what we're seeing is that the shared memory option for coarsening is significantly faster. It's it's about 7 times faster on shared memory than using MPI and distributed memory systems. So that's why the first step, we employed a shared memory approach. We don't, as I said, we don't touch the embedding part. That's generalizable to any method. We want to keep the high productivity advantage that MILE provides. And so, but we do note that this is compatible with, so if you have an embedding method, a graph representation learning method that is compatible with scalable CPU or GPU training, that is a base embedding method that you can apply, and you can take advantage of whatever GPU high performance computing support that you have in that context. But we don't place any requirements on the base embedding for this. For refinement, it turns out that distributed learning actually offers a significant advantage. We rely on GPU-based distributed training enabled by Horovod, implemented. So Horovod is a open source toolkit that Uber originally started using, but then open sourced it, and then it has been enhanced by several community members in the high performance computing community. And the idea that we rely on, a couple of things that distinguish what distributed MILE does from MILE is that we use a parallel sampling method for some of the training, and also rely on mini batch training as opposed to training on all the nodes, which facilitates parallelism and allows independent nodes to proceed without requiring tight synchronization. And again, our metrics are very similar. We compare MILE versus distributed MILE on a small cluster, 4 machines, and each machine has this particular configuration. We looked at the same data sets we were looking at before. And what we see is that there's really no difference between MILE and distributed MILE in terms of qualitative performance on most of these. But we do see, and we're showing end-to-end running time here, but we do note that the base embedding is the same. And so there's only so much you can improve. If you go back to some of what we've learned from Amdahl's law and so on, you're only as fast as your slowest component within a pipelined architecture or within a system. And so if our base embedding takes time, this is end-to-end wall clock time that I'm showing on the figure on the left, there's not much improvement you can get from those steps. So now, so that's a fact, but we still see significant improvements. Again, the time here is on log scale, so between these methods. And so just so you see SDNE, the original SDNE with MILE is over here I think, yeah. So we see the same, we see the same improvements across the board. So MILE SDNE is the light green over here, and distributed MILE is the dark green. And similarly, NetMF, the MILE is over here. The distributed MILE, you see a significant drop. Again, this is an orders of magnitude improvement given the log scale of time here. But if we look at the individual steps, coarsening and refinement, we can characterize their improvements more specifically. We see up to a 10x improvement in coarsening. Remember, this is shared memory. And we only had about, I think, 14 computational nodes that we could use in the shared memory setup out of the 28. And then in the distributed context, because of GPU, the GPU, we could see a 58x speed up in what we were proposing in the distributed MILE environment versus standalone MILE using one of the nodes. So the key takeaways: embedding techniques often do not scale on log graphs. MILE is a framework, it's a system. It scales existing techniques in a method agnostic manner. It can also improve the quality of generated embeddings in the process, but really allows orders of magnitude improvement. And so code is available at this GitHub repo, and I'll be sharing the slides with Ravi and Karthik later, so you don't have to worry about that. And distributed MILE, distributes the two phases, coarsening and refinement, and it relies on a new parallel algorithm for graph coarsening and a distributed training paradigm using MPI with high scaling efficiency on those two components. But again, scaling efficiency is ultimately driven by all the components, and we don't touch the base embedding level. And we see improved scalability over MILE with no change almost in terms of the resulting quality. So that concludes my talk. I do thank you for your attention, and I'm happy to take any other questions that folks might have.
Thanks a lot, Srini, again for a wonderful talk, as always. So there are a few questions. So one question is on the applications, right? The question reads something like, could you highlight any relatable application where this is used in the backend? But maybe I'll paraphrase it that, for example, how would any of the large websites that rely a lot on graph data, practically leverage this algorithm, right?
Yeah. So actually, as it turns out, Facebook has a group that has been looking at some of these things, and they've taken some of the lessons learned with MILE. In fact, in distributed MILE, we compared against their architecture as well. So the paper appeared at HiPC, just presented in Bangalore a few months back. And we did a comparison with an implementation that Facebook had, and Facebook's implementation leveraged some of the original MILE ideas in terms of what they were looking at there as well. So that's one sort of example of how this is seeing some kind of use in industry as well. And their system, I forget what it's called, but it's some PyTorch big graph is what I vaguely remember, but it's in the paper, and I'm happy to share that link with whoever is interested. But in terms of other kinds of applications, one of the applications we are looking at next is, we've talked about these kinds of ideas on if you can see my background, I'm part of this new institute called AI Edge, and we're interested in seeing how some of these ideas will can be leveraged in an edge setting, in a distributed edge setting, where each of the edge devices has a part of the model, and how we can federate something like what we're doing here. So that is one. Another direct answer to that question is that we have applied this for doing some kind of location analysis. We have used MILE for doing some kind of location analysis. And so that's another application area. But here's the clincher in terms of answering that question. The clincher is, if you have an application that is using unsupervised graph learning, you can apply MILE and scale it. So it doesn't matter what the application domain is. We are agnostic of your use case. We can scale it. Yeah, go ahead, Karthik. Next question.
So I have a question. So are there network topologies or degree distributions where this could break down? Because a lot of these real networks typically have a scale-free distribution, right? And it looks like it works on a very diverse class of networks, including some really large networks. Right? So from this, I think the protein interaction network is the smallest of your lot. And so are there networks where you think there could be challenges?
I do. I mean, so if you have a mesh network, it'll still work. It'll still provide a reasonable benefit. But it will essentially default to one of the graph partitioning methods in terms of performance, both qualitatively and quantitatively. It's not going to offer. So the real thing is, where would this kind of coarsening strategy work well? So on networks where the coarsening strategy works well is where you're going to see the greatest benefit. For mesh networks or highly regular networks that we often don't see in the real world outside of certain types of problem domains, you may not see as much of an advantage over, say, a Metis or a Grackless or a Markov clustering algorithm approach. Yeah. I mean, that's a great question, though. I mean, and one that we are looking at. I didn't have time to talk about this, but some of the things we're looking at right now are, how can this extend to heterogeneous networks? And how can we leverage better graph convolution network methods? So one method that we are thinking about using is, how can we take advantage of that structure more by looking more exactingly at higher order interactions. For example, Priyesh, Ravi, and I have some work that we've been exploring, and it would be very easy to substitute that approach for what we're using right now, which is essentially vanilla GCN.
So I have a question. Can I ask?
Yeah, go ahead.
Yeah. So I will just was thinking about it, right? So this is whole setup. MILE is for unsupervised thing, right? So we don't have any labels. Is there a way
it can be extended?
Though? Exactly. That's going to be my question. Yeah. So is there a way to inject the label information somehow into the base embedding part alone, and then the rest of the architecture can stay as it is, right?
That's a very interesting. I mean, we've been thinking about how to do the coarsening by injecting it there, but your idea sounds interesting as well, which is there a way? But then so you need to take the labels you had from the original nodes and propagate it down somehow. In order to do that. So you'd still need to apply, you still need to incorporate something in the coarsening phase for that, Ravi.
No,
but we've been,
okay. So wait, one just thinking aloud, right? So one way of doing this could be that whenever you pick a coarsen node, right, in the base embedding, you could just sample a label from one of the original nodes. And when you repeat this, so that would give you Yeah, I mean, you could do something like that, right?
That's a very interesting point. I'd be happy to talk about that with you offline.
Sure.
I think that would be a.
I guess we have a meeting right after the start.
Yeah. No, I think I'd be happy to. I think that could certainly be interesting to look at. Yes. Other questions, Karthik?
Yeah, hi, Himanshu here. Yeah. So I've been listening to some of your responses and especially the last response where Ravi was asking about labels. Now, I'm sort of looking at, let's say, I know protein interaction networks are not large, but they are sort of, because they are made of binary interactions, they are sort of an extension of binary interactions. If one were to sort of take protein interaction networks as well as information from gene interaction networks, gene expression interaction networks, would that be sort of how would you do coarsening? Would you still want it to be label agnostic, or would you want some domain knowledge to propagate? Because there are nodes which are going to be really promiscuous. Right? There are nodes that are going to be what are called moonlighting also. So would that be something like, would labels be important when you're doing coarsening in those cases, or protein interaction network or gene co-expression networks just work fine with your algorithms, with your methods?
So I think, Himanshu, your question has several parts to it. The part where you say that there are these, ranging interactions across these different networks, we have not really considered. I mean, this is something that we are actively looking at. I mean, both with Ravi and also in my lab, looking at how we can support these kind of multiplex networks. And so if you have interactions that span, even within a transportation network, for example, you may have a bus network, a train network, a road network, and so on. How do these sort of connect together? Yeah. So that's a great question, open question, something we're thinking about, but don't have a solution currently. We do have solutions right now currently for directed graphs. Someone's implementing that right now. We do have a solution for, weighted and unweighted, it works naturally. So no problems there. We can handle certain types of bipartite embeddings as well, no problems there. But some of these other things like labeled heterogeneous graphs where nodes have different types, and that would sort of intersect with some of the challenges that would show up in multiplex networks. We don't have a solution for that, but that's something we're looking at next. So happy to talk about that. Yeah.
Very naive question. Let's say I have applied this and done coarsening and learned embeddings from, let's say, a normal human protein interaction network. And I do the same on, let's say, a cancer protein network, right? Breast cancer protein. Now, would the embeddings be different enough for me to inform which of the edges and which of the nodes are the most important ones, or is that a possibility? Like, can we sort of
you can do it, but you'll need to address this issue in that case. So if I go back, am I still sharing my slides?
Yeah.
Okay. So what you're going to, what you're going to have in that case, if you do it independently, running it on MILE independently, is that you're going to have them they may not be in the same embedding space. So you really want to put them in the same embedding space so that you can have a apples to apples comparison. So the idea of doing it separately and then trying to merge, you're going to need to figure out a way to do this mapping. And that can be a little challenging. So you can start with that, but you're going to need to come up with a fix for that. And so there are some approaches that people have proposed, but they are slightly different. They don't apply necessarily to the multiplex setting, which is what you want to apply that to.
Okay. Thanks. Yeah. Very interesting. Yeah. Thank you.
Okay. So I think most of the questions have been answered. There's like one sort of more technical question. I mean, very into the nitty-gritty. So in SEM, when you're combining the D and E node, is there a loss of data or data redundancy? That's one of the questions.
Yeah, so I think for all of them, there is potentially some loss because, but also potentially some gain because it enforces that those nodes are going to eventually be close in representation space. So it's a little bit of a, it can go both ways kind of answer. Now, there have been some theoretical results that show that under certain types of graph spectral modifications, you can actually show some theoretical results. But again, those also make some underlying assumptions that may not hold in real world graphs. So, many of the theoretical results that people have looked at in this space also have some built-in assumptions to them.
And how do you measure closeness in graph space? I think this was a question. So is it, what kind of metrics?
So this is something that we are thinking about. So the easy way to measure closeness in graph space is, how many links or the weights of the links that you need to cross to get from point A to point B. You can use also, from the stochastic flow literature or the random walks literature, you can use commute time, hitting time, how long does it take to get to point A through a random walk process and things like that. You can use those kinds of things to measure graph space. We've tried to keep things simple, but there is a potential for improving our coarsening step if there are certain desirable properties that you want to explicitly account for. We have not done that yet, but that could be interesting. And so if there's a certain geodesic thing that you want to maintain, if the graph, for example, can be overlaid on top of, if you're monitoring a graph that represents, key locations on in a particular town or city or something like that, and there is a geodesic representation, then that could be accounted for in some of the weighting mechanisms and things like that. But we've tried to keep it simple so far. We've not gone and looked at that, but that could be interesting. So yeah, something we have given some thought to, but we don't have, we've elected at this point not to really push forward on that.
Great. So I think that's about it. Thanks a lot, Srini. Once again, very nice talk. Thanks for sparing your time, and I'm sure the audience really enjoyed it. We all enjoyed it too. And yeah, we'll catch you right after this meeting, but hope to see you in person soon rather than later.
Yeah, thanks everyone for the invitation and for the attention. Bye-bye.
Thank you, Srini. Thank you.
Bye.